Evening, everyone. Thanks for coming out to PyData DC. We're about to get started here. So I'm Wilson, and I'll be hosting our event tonight. With us, we have Jacob Tomlinson. He's Senior Software Engineer with NVIDIA, and he'll be presenting on the topic of deploying multi-GPU workloads on Kubernetes and Python. Before we get started, we have a couple of, if I can get PowerPoint to behave, we have a couple of quick announcements. One of our sponsors, MetroStar here, we have a number of open roles in the AI, ML, data science space. If you're interested in these, feel free to check out our website on metrostar.com. And with that, we're going to go ahead and get started with Jacob's presentation. Thanks again for coming out. And if you're interested in speaking at a future PyData meetup, email marketing@metrostar.com. So I'm going to go ahead and turn this over to Jacob.
Great, thank you very much. Let me share my screen. Okay. Awesome. So shout if you can't see my slides, but you should be able to see things. I'm going to like flip around between a few windows as well, because I'm going to attempt to do a demo through this. So we'll see how that goes. But yeah, so my name is Jacob Tomlinson. I work within the Rapids group at NVIDIA. And I thought for a change, when I do these kind of talks, I usually put like a slide about myself in the beginning, but I'm going to try and introduce myself within like the context of the topic that I'm talking about instead this time. So this evening, I'm going to be talking about deploying multi-GPU workloads, data science type workloads on Kubernetes in Python. So hopefully slides like this are pretty familiar within like the data science community. It's got a whole bunch of cool tools and technology that's pretty popular for use within data science and traditional sciences. So I previously used to work in weather and climate for the UK Met Office, and used a ton of these libraries for doing, post-processing of weather and climate data, stuff that had come out of large models, large 4-channel models and doing post-processing. And through that, I kind of got engaged with like the broader PyData community and got involved with trying to accelerate these things and trying to speed up the work that we were doing, which is kind of what we're going to be getting into in this talk. So, as I said, I work for NVIDIA now, and I'm the cloud lead within Rapids, right? So my responsibility is to try and help everybody leverage the cloud as much as they can for doing accelerated science and data science work within the PyData ecosystem. So Rapids is this open source suite of Python libraries, which have a lot of overlap with all the kind of things you find in the traditional PyData stack. But the idea behind Rapids is these are like accelerated implementations of these libraries. They leverage your GPU so that you can get like much better performance, but they match the same APIs that you hopefully all know and love. So if you're a Pandas user, you can come and check out QDF. If you're a NumPy user, you can come and check out QPy. If you're a scikit-learn user, you can come and check out QML. These are all kind of re-implementations of these kind of popular libraries. So instead of the backend being written in Python or C, it's written in CUDA C++ and leverages the parallelism of the GPU. But then from a user side, you're interacting with a Python API, which should look and feel exactly the same. So I've got a few little examples here. A lot of it is you can just switch out your imports. So you can import QDF instead of Pandas, and then it's got read CSV, read Parquet. It's got all the same kind of methods that you'd expect to find in Pandas. It's just these are accelerated implementations that will run on NVIDIA GPUs. Same for scikit-learn. We also have cuGraph that's like NetworkX. There's like a whole bunch of libraries within the Rapids ecosystem that's there to kind of speed up your workloads if you've got accelerated hardware. And I kind of have to show an obligatory slide of how fast things go. Things go pretty fast if you have the right hardware and you're using these libraries. And so you can kind of balance up whether you want to save money on the work that you're running or whether you want your work to go faster. It's a trade-off that you can decide and make. That's the great thing about the cloud. So the other project that I work on is a project called Dask, which you'll have seen on the PyData stack slide. And this is a project I've been involved in for a long time. And Dask is also in the game of accelerating PyData tools, right? But instead of trying to accelerate like the individual tools themselves, Dask is this general purpose library for parallelism, right? So the way that Dask accelerates pandas is it breaks operations up into lots and lots of small pieces and distributes those over either the cores in your laptop or many cores on many servers in the cloud or in some kind of cluster. Right, so if you kind of look at how Dask does this, you might have like a Dask data frame where you've read in some data, and Dask will have partitioned that data into many small pandas data frames, and those can be loaded in and out of memory when they're needed. They can be distributed across different machines, and then it's got re-implementations of all the kind of operations you'd expect to find within pandas, but it works by producing a task graph, right? All the different steps that would be needed to calculate something. So say you've got a large array of data in NumPy maybe, and you want to take a mean. Dask would break that up by taking a mean of each individual array within that overall array that you can see here on the left, and then those intermediate results will be kind of aggregated together, and then the mean will be taken of that. Right? There's all these different re-implementations that lets you spread this work out. And so the great thing about being in this space is we have Rapids, which is trying to take these libraries and re-implement them so that they're much faster, and then you've got Dask, which is taking these libraries and blowing them apart, distributing them across many machines. And if you combine those two things together, you can then get distributed accelerated computing, which is kind of where our focus is within Rapids. So this is kind of a diagram of what maybe a traditional data science workload might look like. You know, you load in your data, you can do some model training, you're going to kind of have a look at the data, you're going to visualize it so that you can understand it, and then you go back to the beginning, make more decisions about what you want to do. And there's all sorts of libraries within this space for doing this. If you have a look at the Rapids stack, this is exactly the same. It's just you kind of swap out those individual pieces. You swap out pandas for cuDF, you swap out NumPy for CuPy, Dask is still there, Spark is still there. These tools are still there for being, for accelerating these things and distributing across many machines. And all this stuff is great. There's tons of talks and things you can find out about Rapids. I'm going to touch on it briefly, but the main thing I want to talk about in this session today is about how do I actually get this stuff somewhere, right? I can install these things on my laptop. If I've got an NVIDIA GPU in a machine, I can install these libraries and use them, and that's great. But how do I kind of go beyond that? How do I get to this world of having distributed, parallelized, accelerated like data science calculations? So as an example of that, I'm going to take a little XGBoost workload and kind of walk you through what it's like to run that on. I'm going to do it on Google Cloud just because I have to pick somewhere to run it. And XGBoost is a super nice choice for kind of showing this, because XGBoost integrates really nicely with all the Rapids libraries. It can, it is a GPU accelerated library for doing gradient boosting, and so it works with GPU data, right? So if we load data in through the Rapids libraries, one of the great things about the Rapids libraries and just generally within the Rapids ecosystem is that you don't really want to be copying data around too much, right? One of the kind of downsides to GPU computing, one of the things you have to be conscious of is you don't want to accidentally be moving data back and forth from the CPU to the GPU or whatever. That's the thing that takes the time, right? The GPU is this kind of powerhouse of computation, but to get it's kind of on the end of a piece of string, and you've got to get stuff to it, and you've got to think about having data already kind of being passed to it. So being able to avoid any kind of round tripping or copying data around is really great. And so one of the things we focus on in Rapids is kind of going to other libraries and contributing to make sure that they can kind of pass pointers between each other and keep data within the GPU between operations and things. So within Rapids, we employ quite a bunch of folks within the PyData ecosystem, myself included, and we have some XGBoost folks in the team as well. And so you can use this library with the Rapids libraries, but it also has official Dask support now as of like the latest release, I think, which is like 3.1.0 of and that might be Optuna's version number. Anyway, within XGBoost and Optuna, if you want to do hyperparameter optimization, these things have like native integration with each other now. So you can use Dask to kind of scale out your training and HPO and stuff, which is what I want to show tonight. So I'm gonna run through this little workload, but focus on what it's like to deploy this. So the team that I'm in within Rapids is really spending a lot of time thinking about how do we take our workload from wherever we're running it to whatever cloud platform, and we are we are, NVIDIA basically providing GPUs to everyone, and all of the clouds have GPUs. And so we can kind of have any user pop up saying, I use this cloud, I use that cloud, I want to use this service or to use that service. As long as there's a GPU available, we want to make sure we can get the software in the right place. And, traditionally that's, you make sure you package up your software and you make sure it can be installed anywhere. But then when you get to the point where you're talking about distributed computing and large scale clusters, we're really starting to think about like, well, we want to facilitate anybody that wants to grab a bunch of resource from any cloud and cluster it together, pool it together, and run some kind of large distributed workload. So the first way that we start thinking about that is, can we support Kubernetes? And that's a great leveler across all of the clouds. Everybody's got a Kubernetes service. Can we support the cloud ML platforms that kind of exist within the clouds? So that you have the SageMakers and the Vertex AIs and the ZeroML and those kind of services which are trying to facilitate this kind of machine learning workloads. We want to make sure it's very easy to get Rapids into those environments and make sure that you can do multi-node computing within those. And then we also do care about the kind of more bespoke cloud specific services, whether it's how it's cloud implements VMs or whether they have some kind of batch compute platform or all the different kinds of ways of running things. And so the way we've been tackling that is by building a pretty comprehensive documentation site, kind of showing all the different ways you can get up and running. And we have kind of a growing gallery of example notebooks of how to run through things. So this talk is basically one of those example run throughs. It's kind of hard to try and facilitate everyone right within this cloud landscape, right? It's a big landscape. There's so many different choices you can make for the cloud platforms and all the different tools and technologies you want to use, and we want to make sure that we are kind of easy to use for everyone. So we have to have comprehensive documentation that maybe feels a bit like a choose your own adventure. You kind of read the different platform pages, the different tool pages, and try and cobble it together yourself. So putting together these example notebooks allows us to take a bunch of different opinionated trajectories through deploying these things to give you an idea of kind of what's possible end-to-end kind of thing. But then, oh, you don't use Google Cloud, you use AWS, that's fine. You can swap that component out. Or you don't use Dask, you want to use Spark, whatever, you take out different components, you put in other different components. So as I said, Kubernetes is a great leveler for all of these clouds. And so let's dig in a little bit into how we implement this kind of multi-node, multi-GPU workload on top of Kubernetes. And this is a Dask workload. So in order to do this, we're going to kind of have our Rapids workload running at the top. That's going to sit on top of what we call the Dask operator, right? This is kind of native integration for Dask into Kubernetes. And then Kubernetes, in this case, I'm going to deploy on Google Cloud to show you an example, but you can deploy Kubernetes kind of wherever. You can do it on premise, you can do it on any of the clouds, and that can be sitting on top of your GPU hardware. So I'm going to have a go. I've got backup slides in case this all goes terribly wrong, but I'm going to have a go at doing a live demo and kind of running through what it's like to set one of these things up. Hopefully things will go okay. So the first thing I need to do is have a Kubernetes cluster, right, in the first place. And then that can be quite like a throwaway statement, right? Kubernetes is a relatively complex thing and a steep learning curve. But it's actually pretty easy to get hold of Kubernetes clusters if you need them, if you have access to cloud accounts. So I'm going to spin one up on Google Cloud. And I've got an example command here. I've actually already run this command because it takes 5 minutes. And I don't know if you want to watch a loading bar for 5 minutes. But running this command, I'm just going and saying, Google Cloud, create me a Kubernetes cluster. And I'm explicitly saying I want 2 NVIDIA A100 GPUs attached to each machine, and you have to specify the machine type and which region you want those to be in. But that's kind of all I've specified, and that spun me up a cluster. Now, if I just switch over to my terminal, which you should all be able to see as well, shout if you can't see that, but I should be able to say group control get nodes, and we should see that I have my cluster kind of ready. It's giving me 3 nodes by default. I started this up half an hour ago just so that it was kind of ready to use. And so each one of these nodes has got 2 GPUs that we can leverage within our workload. But you can scale this up. I think the most you can get in a node from Google is you can get 8 GPUs per node. And so if you want to do a much larger workload with many GPUs, you can tweak those numbers. So once we have a Kubernetes cluster, the next thing we need to do, and you kind of have to do this in all Kubernetes implementations, you have to make sure that you've got NVIDIA drivers and the right NVIDIA plugins installed. Now, this is like a pretty easy thing to do. Either each cloud will have a kind of way of doing this. Like Google Cloud is just like apply this manifest file. And if I just run that one now, I got notes over here. Let me copy that. If I run this manifest now, it will apply the driver daemon set to my cluster. And make sure that everything's pre-configured. And so the way that works in Kubernetes is it will start a container on each node in the cluster. That container will have kind of root privileges, elevated privileges within Kubernetes, and it will use that to install the drivers on like the underlying host and make it available for that to be exposed into all the different containers that you're going to run, different pods you're going to run. And then it also installs a plugin kind of into Kubernetes so that Kubernetes is aware of a GPU as like a resource type that it can schedule and be aware of and understand, in the same way that you can set limits on CPUs and memory and that kind of thing. So with that installed, I now have kind of a GPU ready Kubernetes cluster. So the next thing I want to do before I get my workload running is I also need the Dask operator. And this is something that we built out in Dask last year, which allows you to work with Dask clusters as these like native units within Kubernetes. And I'll kind of dig a little bit more into what I mean by that in a second. Let me just switch back to my terminal, and I'm going to install the Dask operator here as well. Now, I've got another window open here. This is kind of the dashboard view onto my Kubernetes cluster, and you can see all of the different pods that I've got running. And as my Dask operator gets installed, we should see that pod appear in the new namespace in a second. Is always the thing with demos. They always have a thing. It'll have a thing. I'm sure it'll appear in a second. There we go. Okay. So we can now see I've got this new namespace called Dask operator, and the operator controller is being installed here. It's pulling down a pod. And what this does is this is effectively like another extension to Kubernetes is controller and Kubernetes is API. So we can have kind of native resources. I can say like kubectl get Dask cluster. And I don't have any Dask clusters at the moment, but it will tell me no resources were found in the default namespace, which is good. It didn't say what on earth a Dask cluster. It said I couldn't find any. So it now knows of this concept of a Dask cluster, and we can use those to then leverage our workload. So a Dask cluster is made up of a scheduler and a bunch of workers, and then we connect a client to it, which will submit work into that cluster. And the operator will handle the provisioning of all of that. We just say, can I have a Dask cluster, please? And it will create all the pods and things that are necessary, and then we can connect to it. So yeah, I've done that. That was great. Now, the last thing I need to do is I need somewhere to like drive my data science session from. I could do this on my laptop, but I'm just gonna run a Jupyter Notebook pod in my Kubernetes cluster. Basically, I've just got a few little config options that I've set on it, which we can talk through. That'll get us in like a nice place to run this workload. So I'm just going to say kubectl apply -f, and it was called /temp/notebook for me. And that's just going to apply a bunch of resources, and we can, once that's finished thinking about it, we can kind of talk through those. If I just have a look through this. So the resources that were in that file are kind of specific to how I'm setting this up for this demo. The main thing I just want is Jupyter, and I want it to be in the cluster, and I want it to be able to affect the cluster, the Kubernetes cluster, and I want it to be able to access other things. But you could be using Kubeflow, you could be using Jupyter Hub, you could be using, there's like a multitude of other ways of getting Jupyter and data science environments within a Kubernetes cluster. I just wanted to keep it simple with just one pod. So the way that I've set this up is it's got a service account is the first thing in here. And that service account has a role, which just says that it can do all the things it needs to do, view the pods, view the services, get logs. And the most important one is it can do all of the things that my Dask operator is able to do, right? So I'm just saying anything in the Dask domain, like let it do all of those. So those two things get bound together. I've also got a little config map in here just to inject a little bit of extra Jupyter config, which I'll need to view the Dasc dashboard. We'll come on to that in a bit. Dask's got an awesome dashboard to help you kind of understand what's going on and what it's doing. We have a service resource in here that's just going to help me put forward the Jupyter pod in a minute. And the last thing here is the pod itself, right? This is my container that's going to be running You know, you can see what name it is. You can see that we've attached the service account here. So that pod will have those privileges that we've defined. But the critical thing here is that we're using this container image, right? These are the official Rapids container images that we publish. They have my motion sensor lights have turned on. 1 second. I'm obviously not being animated enough, and my motion sensor's gone off. These libraries are the Ubuntu-based container with all of the kind of GPU stuff installed, all of Rapids installed. It's got Dask, it's got all the bits and pieces, it's got Jupyter, all the things you need for kind of an interactive data science environment. You can pull this down and run it locally, but we're going to use this as kind of the base of everything in our cluster. Now, from a resources point, I'm saying I want my Jupyter session to have 1 GPU, but I'm then going to like scale beyond that using Dask. And there's a few bit of config in here just to set up the dashboard and things. So all of that should have been applied. If I just slide back over to my thing here, I can see my Rapids notebook pod is now up and running and it's alive. So I should be able to do, I should be able to port forward that. Forward. That one. Right, Rapids notebook. And so if I come back into my browser, I'm just going to move my slides out of the way for a second. If I come to localhost 8899, I should be able to see Jupyter. Now, when I was playing around with this earlier in preparation, and the port forward was being a little flaky, so hopefully it won't be. But okay, I'm now in a Jupyter session. Hopefully that's big enough. Shout if you need me to zoom that in any more. But this is that Jupyter session running in my Kubernetes cluster that I've launched on Google Cloud. I have a GPU here, so if I pop open my terminal and run NVIDIA SMI, this is the like show me info about the GPU command, the NVIDIA SMI. So if I run this, it gives me a little printout just to say what my driver versions are and things. But we can see I have one NVIDIA A100 GPU here, which has got 40 gig of GPU memory and whatever. It's a great card. So I can use this GPU to do some work in this session. But I need to go beyond that, right? The workload that I have in mind is going to be larger than I can run on one GPU. I need more. So let's get that workload. Now we have a whole bunch of notebooks, like I said in our documentation, and I'm just going to download one of them into this session. You can go and find all of this. The links are in the slides. I'll make sure they're shared kind of after this if you're interested. But if I download this notebook and open it up, this is our XGBoost hyperparameter optimization notebook. There's a little bit about Kubeflow in here because that was when we wrote this. So let me clear all the cell outputs just to make sure you can kind of see this and go through. Now, there's a couple of things, this is, like I said, this is the Rapids container. So there's a couple of little bits I just need to add into here. So I need Dask Kubernetes, which is the kind of Python front end for driving the Kubernetes integration. It does have like just pure Kubernetes integration. Like I think if you see on this slide, you can either create things in Python, the way I'm going to in a minute, or you can do it in YAML Kubernetes style if you need to be checking into, GitOps or something, some kind of, deployment system that's based on Kubernetes. So within my Rapids container here, my notebook container, I'm going to just pip install Dask Kubernetes as library for interacting with that. And I'm also going to use Optuno, which is the library I'm going to use for the hyperparameter trials, which is going to be calling XGBoost. So with those extra things installed in my container, the next thing I can do now is actually start my Dask cluster. So let me just bump that version number up because it's a different month now. So here I'm going to say, I want a cluster with the Rapids container image, the same one I've used for my notebook, and I want 4 workers, right? I want 4 GPUs effectively for the workload I'm going to run. And so from the Dask Kubernetes operator, I'm going to import this class, this kube cluster class, and I'm going to instantiate it with a bunch of options. I'm just going to change that to Optuno as well, like that. So I'm going to give this Dask cluster the name Rapids Dask. I'm going to set the image to be this Rapids image. And I need to just specify that this is a Dask CUDA worker, right? This is the GPU version of Dask rather than the CPU version. I'm going to set the number of workers specified outside here. I'm also going to specify that each worker within my cluster should have 1 GPU. And I'm going to set a couple of extra options. So this will just by default, the Rapids container starts Jupyter as kind of a sub-process. We don't need that, so I'm going to turn that off. And I'm going to make sure that all of the workers get Optuna installed at runtime as well. This is a nice feature of both the Rapids and the Dask containers, actually, is that you can use environment variables, extra pip packages, extra conda packages, extra apt packages, I think, and it will install things at runtime as the container starts. So I've instantiated this class, and you can see it's thinking for a minute. And if I come back over to my Kubernetes dashboard, let me just simplify this a little bit so we can see what's going on. There we go. So you can see I've got my notebook pod here, but because I've instantiated that class, I've created a new Dask resource. If I actually just go dsk, we can see that I have one Dask cluster called Rapids Dask. If I just come back to the pods, that Dask cluster, the operator controller has seen that Dask resource be created, and it's gone, okay, I need a scheduler, and you said 4 workers, so here's 4 workers. It's just created a service for those. So there will be, we should see under services, there's the Rapids Dask scheduler service. So they're going to be using this service to talk to each other, and everything can kind of talk. And because I ran the notebook within the Kubernetes cluster, it can also connect to that service. You can also port forward it and kind of access it from outside as well. But that took a few seconds. Now we have this cluster object instantiated. And if I just have a look at this cluster object, Dask has some really nice kind of HTML views onto things. And I can drop down and say, okay, this is a kube cluster. It's got 4 workers. I can find out information about the scheduler. I can drill down each worker and have a look, and I can see, oh yeah, great. Each worker has got an NVIDIA A100 GPU, just like the notebook, 40 gig of RAM. The host has got, a lot of memory and things. And then one of the nice things that Dask does is it lets us connect. We have to connect a client, right, to be able to submit work to the cluster. But we've created this cluster through an object. We can just pass that straight to the client. This will also take like an address, this address here, if you have created it by other means. But it's great. You can just connect straight to that cluster. And if I just have a look at the client object, same kind of look in repra. It's actually the same. You can see it's nested, the same one in there, but it's got this really nice new launch dashboard in JupyterLab button. And if you've got the Dask JupyterLab extension installed, which the Rapids container does, if you click that, it will kind of pre-populate things. So we can go into the Dask extension here, and these are all like really useful graphs that you can see kind of what's going on within your Dask cluster and see what it's doing, and it's really useful for development and debugging and things. So I'm just going to open a few plots and kind of arrange them just the way that I like to arrange these things. So let's have a look at GPU memory, GPU utilization. Let's have a look at progress bars for the workload we're going to run. Let's have a look at cluster map, which kind of shows us a hierarchy of our cluster. And we'll have task stream, which will show us things kind of whizzing by as they run. So if I slide these around a little bit so we can still see the notebook, I might just collapse that out of the way. Let's go like that. Cluster map, give you a bit more space. Slide that way. Right, I spend too long arranging these windows, but there we go. This is all quite zoomed in as well. I wanted to make sure it's nice and big for the talk. But we've got all kind of plots. We can see what the Dask cluster is doing. And now we can think about giving it some work. So, if I run like a little toy example here, I can, do some hyperparameter trials. Let's say we want to run 100 trials, and we're going to use Optuna to do this with XGBoost. Using Dask. Now this is using the kind of new feature in Optuna, which lets us use Dask as kind of the memory storage for what's going on in the hyperparameter search. So things will be distributed onto the GPUs, but Dask will be keeping track of kind of the progress of the HPO, and Optuna can kind of use that to coordinate between the different GPUs. And so doing it this way, we could, if we wanted to, just keep scaling this, adding more GPUs and distributing the work across. Now, let me just run this. We should see things maybe flicker to life a little bit for a second. And we can see, that ran pretty quickly. We saw the cluster do a little bit of activity, and it's given us a reasonable output here. And if we have a look at what these graphs have done in this, we can see the task stream here. Each one of these rows in my task stream is each of the GPUs within my cluster. And you can see if I kind of hover over these boxes here, each one of these is a different function that was called kind of within this loop. This is client.submit is submitting these optimized calls into the cluster. And so we can see those kind of get loaded, how long they took. You know, this is a reasonably small kind of toy example compared to something larger. It's kind of what you need for a talk, but you can see these are being distributed. Each of the GPUs is kind of doing these in parallel. Kind of is nice packing as well. Like if the cluster was being inefficient, there'd be a lot of white space and things, which is good that we don't see that. So let's scale this up a little bit. Let's do something a little bit larger. So this is kind of the same problem again, just a little bit larger data. I'm just going to change that number to 1,000 just to make this run for a little bit longer. And now if I run through this, we're going to do a bunch more trials, and we should be able to see our cluster's going to start picking up work. The progress bar is kind of making its way across as it's doing its HPO. Our GPUs are being utilized. As I said, this is a pretty small problem. So we have quite a lot of GPU memory here. We've got 160 gig of GPU memory. We're only using about 4 gig of it with the data set that we've got here. And these progress bars are kind of just ticking along as work's being distributed. This is the kind of thing that without a setup like this, you would be doing sequentially, right? You'd be doing one trial after another. Whereas being able to scale out to a Kubernetes cluster, we can just keep adding workers, keep cranking things up, and really spread this workload out. And so it allows folks who would want to do this kind of hyperparameter search to not be limited by the computation when you're trying to, you know, find the right options for your model. So this is kind of getting towards the end now. Oh yeah, I didn't talk about the cluster map. This is just a little map showing each of my 4 workers, each of my 4 GPUs. And this, hopefully, I don't know if you can see it in the Zoom meeting, but there's like little tasks flicking back and forth from the scheduler in the middle. So if we have a look now, we should have some kind of better parameters from all of our different hyperparameters here. And we can, you know, visualize those with different plotting functions. So yeah, this is a toy example. I actually converged on something pretty optimal quite early on in that, and I ran quite a lot of trials that I didn't need to run, but you know, on large data sets and different problems, this can really scale you out. So that was kind of it for the example. Once things are all finished, I can tear my cluster down again. So I've just got let me copy this off my clipboard as well. I've just got this command where I can say, you know, gcloud containers delete my Kubernetes cluster, and that would just bring all these resources down again once I'm done with them. So this is just, you know, this is just one way of being able to run a Rapids workload. You know, I've taken a few opinionated choices here. I've kind of chosen Google Cloud as my platform. I've chosen Kubernetes as kind of the layer to run things on. I've chosen Jupyter to drive it. I've chosen to deploy Jupyter as a pod on my cluster. I've chosen to use Dask as my kind of distributed engine. I could make more choices, right? Once I've got my model and it's trained, I would probably want to put that into production somewhere. I might want to serve it up. Maybe I want to use KServe, maybe I want to use Triton Fill or something. You know, there's lots of different servers for serving up models via an API. And this is kind of what I was saying at the beginning. There's like so many different choices you can make about how to run these ML workloads. The thing that we're trying to achieve in Rapids is just kind of, if you've got NVIDIA GPUs and you want to do data science problems, we're just trying to make like that as low friction and as well documented as possible. So whether you're running on one system and you want to use like a local Dask cluster with however many GPUs you might have in a server, or whether you want to use Kubernetes, you can make all those different choices. It just depends how it works for you. So yeah, if you want to go check out all of our examples, you can find those on this URL. We're actually in the process of kind of refreshing this as well. Oh yeah, that was my backup screenshot in case my demo didn't work. So yeah, Rapids is being used in a whole bunch of places. Hopefully, if this has been interesting to you, you might want to look at using it where you are. But also, we're an open source community, right? Where all of these libraries are written in Python, plus CUDA. You can find it on GitHub. You can come and contribute if you want. If you find bugs, you need help. We have a whole bunch of different places where you can kind of come and find information. We've got lots of documentation, and we've got like Slack channels, forums, all that kind of stuff. So yeah, I hope that was kind of a nice overview of what we've been working on and how you can run like a large HPO workload like this on Kubernetes. And yeah, thank you very much for your attention. Happy to take questions and generally just chat.
Awesome, thanks, Jacob. So I believe everyone should be able to unmute themselves. If they have questions, feel free, or you can drop them in the chat, whatever works best.
Do you, and thank you for the talk. Do you have, can you talk a little bit more about the difference between like the Dask job and the cluster? I think I saw a slide there, but it went quickly. I know there's like options for, I think the Dask operator for like creating a Dask job versus like a cube cluster and all those, and like what the difference between those are.
Yeah, sure. So I mean, like Dask has this concept of like a cluster, right? So that's a scheduler and a bunch of workers, and there's like all sorts of different ways to deploy these, and we have lots of different tools that let you deploy them on Kubernetes or natively on cloud or on an HPC system or on your laptop or whatever. We have an SSH implementation that lets you SSH into other machines and leverage those, which is actually our most popular way of deploying, it seems, quite often. So the thing that I've kind of been, so I'm trying to go backwards through my slides to find the one that you're referencing, this one. So you have this like Dask cluster, you can get that in all sorts of different ways. And then within like the context of this talk, I've just been talking about the like Kubernetes implementation. And there's like a few things that we've kind of done, a few like abstractions that we have within the Kubernetes implementation of Dask. So we have a Dask cluster object, which is this like scheduler and workers like grouped together, and it makes sure that they all come up together and that you can access them. We also have this worker group resource, which is like an additional thing that you can add to a Dask cluster. So say you have some big workload where you know one function call is just going to like blow up memory for a second, and then it's going to collapse back down again, and you can move on. You could add an additional Dask worker group and say, okay, I want a couple of Dask workers that have got 10x memory of all the rest. And I want to like, you can annotate things in Dask and say, right, I want to direct those exploding steps to the workers that can handle it, right? So there's a facility for that. And then we also have another task type called Dask job, and that's kind of more of a batch style job. So, you know, everything I've done here was like interactive, right? I launched Jupyter, I kind of drove the session from a notebook. I created a Dask cluster. It was all very manual. I was like the inefficient thing in the loop there, right? Like driving things and running things along. A Dask job is meant to be more like a thing you can fire off. You can say, right, I have a notebook in a container, and I want to run that on my Kubernetes cluster, and it will like create a sidecar Dask cluster, run the notebook, kind of hook it into it. It pre-configures all the environment and everything. That notebook can like run all the way through, leveraging the Dask cluster, and then when that pod finishes, the Dask cluster will be like automatically torn down again, which is really great if you want to be able to like submit things, and if you're sharing a cluster with many people, or you have like an auto scaling cluster, it's a great way to like save cost within like something you can submit, or maybe something you might run nightly. Does that kind of answer your question?
Yeah, and I guess the other thing, I'm not as familiar with Dask. Is it traditionally like a single tenant type of workflow where like one user creates a Dask cluster to run their GPU, and usually it's not as much more about like multi-tenant or like, you know, multiple people running that same cluster?
Yeah, I mean, typically, like Dask itself, the scheduler, when you submit work to it, it will just kind of treat things like a queue. If you keep sending task graphs to it, it will just process them one after another. If you're a single user connecting to that cluster and submitting things, you're probably not going to tread on your own toes. If you have lots of people coming in and submitting things, like it works, it's possible, you'll be queued and everything, but you might not have like a great experience doing it that way. So one of the things that we really try and strive for is to make the Dask cluster itself a little thing that feels really ephemeral, right? It's just like a little runtime component that just kind of exists for the time that you need it. So like in this example, the Kubernetes cluster was like the big heavy thing that you had to get up, and I mean that was only one command, right? But like that was the big heavy thing that you had to get up and running, and might be multi-tenant and might have a lot of people on it if you're kind of doing Kubernetes at scale in your organization. And then maybe everybody is like firing off Dask clusters. They take like a second to appear. You can submit a load of work. Maybe they only exist for the duration of your job, and then they go away again. And the Python function here, I know this is a little bit small, but you can see here I'm assigning like cluster equals kube cluster. That's also actually a context manager. You can say like with kube cluster, do a whole bunch of stuff. So you can just have like a Dask cluster as like just a chunk of your workflow if that suits you. So I always try and encourage folks to like, don't think about Dask as like maybe a traditional cluster. It's just like a little thing to help you pull together a load of resource for the time that you need it. And then you can release it again and somebody else can grab it.
Great, thank you.
Sure.
So a question I would have for anybody that's either newer to data science or maybe is looking to try this out for the first time and isn't as familiar with setting up their own Kubernetes cluster, what would be some recommendations you would have for getting to learn how to work with things like Rapids and Dask in an easy to stand up environment?
Yeah, sure. So I mean, if you go to tutorial.dask.org, I think if I go to tutorial.dask.org, there's like a whole bunch of notebooks here that will walk through Dask. We tend to run this tutorial like semi-regularly as well. I spotted Natty's here actually, who's another Dask maintainer, and we gave a tutorial together at SciPy last year. But there's like a bunch of notebooks in here that you can run through, and these walk through kind of, this is the like chunked distributed side of things, right? It's talking you through how to load in. Maybe I've got, sorry, it's a bit small. Using the Dask data frame to read in, a large chunked Parquet data set from S3 or something, and then do your kind of operations. The tutorial will walk you through all of these different pieces, and then Rapids. If you go to rapids.ai, we have a whole bunch of resources here as well for like the GPU side of things. So if you go on like get started, there's like lots of links and things out to notebooks and tutorials and like installation and all of that kind of stuff. And there's a bunch of material in here as well about how to do the GPU stuff and then how to combine that with Dask to do the distributed GPU stuff.
Awesome.
So they should be on that slide. I'll make sure I'll tweet these slides out later or something so folks can find those.
Nice, sounds good. Any other questions anyone has on Jacob's talk?
If anybody watching back does have any questions or anything, feel free to contact me on the details there. Always happy to just chat on Twitter about this kind of stuff.